Welcome to the deep dive, everyone. We're doing something a bit different today.
We really are.
Yeah, so a listener actually sent in this highly specific technical data sheet. And I mean, at first glance, it's for an industrial paste.
Right, which sounds, maybe a little dry on the surface.
Exactly. It's a product from JetLube called KOPR-KOTE Arctic Drill Collar and Tool Joint Compound. And I know a technical sheet for gray paste seems incredibly niche.
Oh, totally.
But our mission today is to dig into the fascinating physics and engineering that are hidden inside these specs. We're going to explore how this simple-looking gray paste actually solves some massive mechanical paradoxes deep underground.
Yeah, and it's a great choice by the listener because this is a staple in a really high-stakes environment.
Right.
We're talking about water well drilling and HDD, which is horizontal directional drilling. I mean, for over 3 decades, this stuff has been the premier standard.
Which is saying something in that industry.
Oh, absolutely. Because when you're pushing thousands of feet of steel pipe through solid rock, fluids in these thread compounds are, frankly, the only thing standing between massive steel joints and total catastrophic failure.
Right, and I want to talk to you, the listener, directly for a second, because by the end of this, you're going to have this amazing aha moment. We're going to show you how sometimes, to make things work smoothly, you actually need to intentionally increase friction.
Which sounds completely backwards, I know.
It really does. Okay, let's unpack this, because the primary function of this compound just feels like a typo when you first read it.
It really jumps out at you.
Yeah, it says KOPR-KOTE Arctic is designed to prevent, quote, excessive circumferential makeup, which basically means it stops the pipe joints from over-tightening.
Exactly.
But wait, isn't a lubricant supposed to make things slippery? Why do we want friction? I mean, if I put heavy grease on my car's lug nuts, I risked over-tightening them because I took the friction away?
Right. Standard garage mechanics.
Exactly. So how does this industrial paste defy that? It's almost like a Chinese finger trap or maybe a seatbelt.
A seatbelt is actually a brilliant analogy.
Like, it allows completely smooth movement right up until extreme pressure is applied, and then it just locks down to protect the system from, well, crushing itself.
What's fascinating here is how the compound dynamically responds to that pressure. So when the rig first screws 2 pipes together at the surface, it acts like a normal, high-quality lubricant.
Nice and smooth.
Right. The threads slide together effortlessly until the shoulder faces of the joints mate perfectly. But then you send it underground.
And the physics change.
Drastically. Once that drill bit hits solid rock, the rig at the surface is still twisting, fighting the resistance of the earth. So that rotational force travels all the way down the pipe and tries to screw those joints together tighter and tighter.
And if they just keep tightening?
Well, eventually you hit the metal's yield point.
Which is bad.
It's disastrous. Yield is the point in metalwork where it stops flexing and permanently deforms. And you have to remember, these joints aren't just holding the pipe together.
They're a seal, right?
Exactly. A high-pressure hydraulic seal. They're pumping heavy mud down the center of that pipe to clear out rock cuttings. If the joints over-tighten, the metal stretches, the seal breaks, and you lose your hydraulics.
Oh, wow.
Yeah. And then that high-pressure fluid just acts like a water jet, cutting right through the steel. The pipe snaps, and you've lost millions of dollars down a hole.
So this paste is literally the fail-safe that prevents that.
It is.
The data sheet says that as stress levels rise above 50% of the metal's yield, the friction factor of the compound actually increases. It limits that downhole makeup.
Right. It triggers based on the stress.
It maintains full hydraulic joint efficiency, letting the shoulder faces mate without standoff or deformation. And they actually quantify this. They list the friction factor at 1.15.
Yes, relative to the API RP5A3 standard.
So a 1.0 would be your baseline API standard compound, and a 1.15 means this paste intentionally creates 15% more drag.
Exactly. It creates drag precisely when the metal needs it to survive.
Okay, here's where it gets really interesting for me. Because we know what it does under pressure, but what is actually in this stuff?
The physical makeup is wild.
It really is. The sheet says it's the more pumpable, sprayable version of their standard KOPR-KOTE. It's an NLGI grade 1 with a penetration rating at 77 degrees Fahrenheit of 310 to 330.
Which basically just means it's about the consistency of tomato paste at room temperature.
Right. But then you look at the ingredients. It's packed with copper flakes and graphite. The density is 9.6 pounds per gallon, which is significantly heavier than water.
Oh, yeah, it's dense.
So how does that work? It's full of copper flakes, yet the spec sheet says the color is gray. and it's designed for spray and pump equipment.
It seems contradictory.
Right. It's culinary physics. It's like trying to make this heavy, chunky peanut butter that you can somehow spray out of an aerosol can perfectly smoothly. How do the heavy metal flakes not just sink to the bottom of the bucket?
If we connect this to the bigger picture, it's all about the base components. The sheet lists an anhydrous calcium thickener and a low-pore petroleum fluid.
Okay, break that down for us.
Sure. So the petroleum fluid provides the actual lubrication, but that anhydrous calcium is the magic. It acts as a thickener, creating this microscopic three-dimensional matrix. It's literally scaffolding.
Wow, chemical scaffolding.
Exactly.
Yeah.
And it perfectly suspends that solids package, the copper and the graphite.
Yeah.
That's why you can pressurize it and pump it without the metal falling out of suspension.
And the color.
The gray color is just because graphite is visually overpowering. The copper is in there, but the graphite just dominates the look of it.
But the copper is doing the heavy lifting, right?
Absolutely.
Mm.
Which brings us to a huge environmental point on this sheet. It notes the compound is unleaded, contains no zinc, and conforms to Assembly Bill 1953.
Right, which was that California law about lead in water systems.
Exactly. Historically, drillers used lead-based compounds because lead is soft and smears perfectly to seal threads. But pumping lead into the earth, especially near water wells, is obviously a terrible idea.
Yeah, total non-starter these days.
So they had to remove the lead and zinc. Instead, they used this solids package of copper and graphite. When the steel threads try to grind together under massive torque, which usually causes them to cold weld and tear each other apart, a process called galling.
The copper steps in.
Yes, the copper flakes literally plate out on the steel. They form a physical barrier that prevents metal-on-metal galling.
That is just incredible material science. But wait, the environment where they use this stuff? The data sheet lists some edge cases that seem insane.
The temperature ranges alone are staggering.
Right. The service rating is from negative 65 degrees Fahrenheit, which is negative 54 Celsius, all the way up to 300 degrees Fahrenheit.
It's an unbelievable swing.
So what does this all mean? It's like engineering a jacket that keeps you perfectly comfortable during an Antarctic blizzard, but then, doesn't melt when you walk inside an industrial pizza oven.
That is actually a great way to put it.
And the base oil pour point lets it stay fluid at negative 65, while the dropping point where the scaffolding melts is over 300 degrees. The flash point is over 320 degrees. And at 212 degrees, evaporation loss is less than 3%.
It has to survive those extremes. Because deep down in the bore, the friction heat is immense.
And the physical conditions are just as extreme. Higher speeds, higher penetration rates, long horizontal holes, harder rock formations. The sheet specifically mentions that it sticks to wet joints and has unequaled resistance to downhole makeup.
Right, it's incredibly tough.
But then there's an instruction here that I need you to explain. For these extreme applications, it says rotary shouldered connections should be made up an additional 10%. If the whole point is to stop the pipe from over-tightening, why on earth are they telling drillers to apply 10% more torque right from the start?
This raises an important question about the realities of fieldwork versus lab theory. You have to picture a long horizontal hole. The rig is turning the pipe at the surface, but the bit might be stuck on hard rock miles away.
Okay.
So the entire pipe acts like a giant twisted spring. The rig might turn 5 times before the drill bit at the bottom turns once.
I can't even imagine the tension on that steel.
It's massive. And when that bit finally breaks through the rock, all that wound-up energy violently releases. The pipe whips and vibrates. If those joints aren't pre-tightened that extra 10%, that whiplash can literally shake the joints loose before they ever reach the 50% yield point to lock down.
Oh, I get it. So you're tightening the seatbelt extra hard before the crash even happens because the road is so bumpy, it might just unbuckle itself.
Exactly. You need that initial tension to survive the vibration.
That makes total sense. But speaking of lab theory versus field work, there's a big caveat about that 1.15 friction factor.
A relative warning.
Right. It says the friction factors are relative. But looking at the tests on this sheet, they are hardcore. The 4-ball weld point is a massive 800-kilogram force.
Which is an incredibly brutal test.
Yeah. They basically just smash steel balls together with the grease and spin them until they weld from the heat, right?
Exactly. And 800 kilogram is elite pressure resistance.
And the copper strip corrosion is a 1A, so it doesn't even tarnish its own copper. With numbers that solid, why call the friction factor relative?
Because a pristine lab is nothing like a drilling rig. On a rig, you have variables like pipe size, thread geometry, and most importantly, mud contamination.
Ah, right. If you drop it in the dirt, the math changes.
Exactly. The spec sheet is warning operators that despite the incredible lab specs, they have to rely on their own experience and intuition when setting the final torque.
There is one environmental condition, though, where experience can't save you.
The chemical exception.
Yeah, this really stood out to me. Do not use with invert or high pH muds. It actually tells you to use a totally different product, like JetLube 21 or Extreme. Why would high pH mud defeat a paste that can survive negative 65 degrees and 800 kilos of weld force?
It's the Achilles heel of that anhydrous calcium thickener we talked about. High pH, highly alkaline drilling muds chemically attack that calcium matrix.
Oh, so it attacks the scaffolding.
Exactly. Through a process called saponification, the high pH mud literally tries to turn the calcium grease into soap.
Wait, into soup?
Literally into soap.
Back
The
up.
3D matrix collapses, the scaffolding dissolves, and all that copper and graphite just wash away, leaving the steel totally unprotected.
Wow, so you have to switch to a paste with a different chemical base that won't turn into soap.
Precisely. It's a great reminder that no single engineering solution is entirely bulletproof in every environment.
This has been such a wild ride. Just to summarize for you listening, we took this simple technical data sheet for a gray industrial taste and discovered this incredibly intricate world of material science.
It really is a masterclass in engineering.
We looked at how JetLube's KOPR-KOTE ARCTIC uses copper, graphite, and smart physics to intentionally increase friction under extreme stress. It protects drill joints across insane temperature ranges and massive horizontal distances.
And it locks them down just before they tear themselves apart.
Exactly. I mean, who knew thread compound was so intense?
Well, it leaves us with a really fascinating final thought to ponder, I think.
Oh.
Yeah, I mean, most of you listening are probably never going to operate a massive horizontal drill rig, right?
Probably not.
But exploring this compound, this idea that you intentionally increase resistance to prevent a catastrophic failure, it really forces us to think about the invisible thresholds in our own lives.
What do you mean?
Well, where is the 50% yield mark in the structures we rely on every day? Think about it. What hidden compounds, whether they're physical, digital, or even social, are out there quietly doing the paradoxical work of increasing friction?
Just enough to keep things stable.
Exactly. Increasing friction just enough to keep our own complex systems from spinning out of control and tearing themselves apart.
Wow, that is a heavy thought to leave off on. Sometimes you actually need the friction to hold it all together.
You really do.
Thanks for joining us on this deep dive. We'll catch you on the next one.